Welcome to example 11 in review of statics. The question reads, determine the normal force, shear force, and moment at a section through point C. Okay, so in terms of givens, you're not given much. You can, if you really want to write something down, like you can, for example, write, okay, there's a pin connection at point A. So we're going to write that. Pin at A. What does the question want us to find? Well, it wants us to find the internal reaction forces, or the internal forces, or the internal reactions at point C, and that's basically just our moment at point C, our shear force at point C, and our normal force at point C. From that, you can move on to the free body diagram, and if you draw this thing out, it'll kind of look like so. So you have the bottom bar, you have this other bar that comes out like this, you have this type of pulley thing, or a pulley. You have, if we label the points, you have A, C, and I think B is around here. So this is B, this is A, this is C. You also have a rope coming around like this. Perfect. Now you can label the dimensions. In terms of dimensions, this from here to here, and then also from here to here, this is 0.1, this is 0.6, and then draw like that. This is 0.7. Oh no, this isn't 0.6. This is, oh my god, this is 0.5. This is 0.75. This is 0.75. That is also 0.75. And this is all in meters, but I don't want to write it down to like clutter stuff. Okay, we can move on to the apparent external forces and then move on to the reactionary forces. In terms of apparent external forces, I only see this 8 kilonewton force, as well as this tension force up here caused by the rope being like held at point B. What other forces do I have? I don't think I have any else. You do have the reaction forces, as we said, also at AY and AX caused by the pin. So we're going to draw all of that down, our diagram. Okay, and from this, you can find everything, all these forces. How? By taking some moments and sum of forces. If we move this lovely guy to the side over here, you can easily tell, or I actually won't do it because we've done this a lot. So if you take, but I'll show you. If you take a sum of moments about point A, it gets rid of AX, it gets rid of AY, 8 kilonewtons causes a moment, and tension also causes a moment. For the 8 kilonewton force, your R is going to be this distance right here, which is, I think, 2.25 meters. Yep, it's 2.25 meters. For your tension force right here, your R is going to be this length right here, and this is 0.6 meters. And if you're having trouble seeing why the tension force will cause a moment about point A, if you imagine if you like free the body and remove all the constraints from this structure, what will this tension force do if there were no constraints? Well, it would try, if you can imagine it, try and rotate it around this axis, right? It will try and rotate it around point A if there were no constraints. So that is why it causes a moment, and this is the R. But yeah, so if you do that, I'll quickly jot it down. So sum of moments about A, and you say this is counterclockwise is positive, you have 0, you have 8 kilonewtons times 2.25 meters. It's a positive counterclockwise moment, minus 0.6 meters times tension. From this, you're going to find the tension is equal to 30 kilonewtons, right? From sum of forces in the y direction, you're going to find that AY is equal to 8 kilonewtons, and AX is equal to 30 kilonewtons. Perfect stuff. From this, we have T, we have AY, and more importantly, we have AY and AX. Therefore, we can section the beam. We can take this section, a closer look at AC, and then if we section the beam, we're going to have an M and V, and that's basically what the question is asking us for. And we can easily find this since we know AY and AX, right? Okay, so we're going to take a look at section AC. So section AC. Let's keep this in frame. This is point C, A, Dimensions are from here to here. This is 0.75 meters. You have a y, ax, and then you have, let's say, NC, you have VC, and you have MC. Perfect. And our goal is to try and find these three. Okay, how am I going to do this? Well, you're going to do it via sum of moments as sum of forces, as you should know by now. But I'm going to start with sum of moments. But the question is, do I want to take a moment about A, or do I want to take it about point C? Well, let's quickly analyze both options. If I take it about A, I'm going to get rid of AX, I'm going to get rid of AY, but an NC will not cause a moment because it's parallel to the R, to the distance, if this is your R. VC will cause a moment, right? And MC I also have to include in my calculations. So from this, what do I have? I have two unknowns. This isn't helpful for me. This isn't going to help me at all. So that is a no-go. I do not want to do that. You can, but then substitute this equation later on. But why would you go through all that hassle if you can just take the moment about C, VC goes away, NC goes away. You have to deal with MC, right? AX does not cause a moment because it's parallel. AY causes a moment. So what do you have now? This is a known. This is not an unknown value. You have it right here, right? So if you do this equation, you're going to find MC. And I'll show you how that's done right now. So again, if we take a moment about C, counterclockwise moment, this moment is clockwise, so it's going to be negative. So negative MC is equal to, is not equal to, but a plus AY times 0.7 meters. AY, as we determined, is 8 kilonewtons meters. AY, as we determined, is 8 kilonewtons. And if you solve this, you're going to get that MC is equal to 6 kilonewton meters. And there, you have one of your answers, basically. And from this, all you have to do is take sum of forces in the y direction, sum of forces in the x direction to find VC and NC. And if you do that, you're going to get that VC is equal to negative 8 kilonewtons, and NC is equal to negative 30 kilonewtons. And even if you want to look back at it, it kind of makes sense as well, that we did not, that these directions are wrong. Basically, since it's negative, it actually means VC acts like this and NC acts like this. Because this beam is in equilibrium, it doesn't make sense to have two forces. The only two forces acting on the beam are left. That means the beam would go left, right? But if you have a 30 kilonewton force going this way and a 30 kilonewton force going this way, and similarly a 8 kilonewton force going this way and 8 kilonewton force going this way, everything's in equilibrium, everything is having fun, yeah? Okay, that's that.